I'm Professor Selçuk Toprak from Gebze Technical University, and today I will be talking about effects of ground strain and pipeline orientation on pipeline damages during earthquakes. I would like to acknowledge my colleagues, co-authors, Engin Nacaroğlu from Pamukkale University, Muhammet Ceylan from Gelişim University, and Tom O'Rourke from Cornell University. The seismic performance of water systems is critical to the resilience of the communities they serve. Ground displacements caused by earthquakes impose strains in pipelines that may result in pipeline damage as well as the disruptions in vital services. In general, ground displacements caused by permanent ground deformation, such as lateral spreading in liquefaction zones, are significantly higher than those caused by transit ground deformation associated with seismic waves. Permanent ground deformation damage tends to result in greater pipeline repair numbers and service interruption effects. Loss estimation methodologies frequently use correlations of pipeline repair rates versus a parameter representing seismic demands. Repair rate is the number of repairs divided by the length of a specific type of pipelines in the same area. The most common parameters representing seismic demands include peak ground velocity for transit ground deformations and ground strains for permanent ground deformations. Existing methods either do not account for the orientation of the pipeline within the ground strain field or provide only for an approximation of orientation. Bozu and O'Rourke proposed a probabilistic way to account for the relative orientation of pipelines with respect to maximum ground strains. In their approach, the expected value of the ground strain in the axial pipeline direction is calculated assuming that the probability of a given pipeline orientation relative to the direction of principal ground strain is uniformly distributed. Toprak, in 2016, Toprak et al. Performed a pilot study to account directly for pipeline orientation with respect to ground strain fields in terms of pipeline damages by using the Avonside neighborhood of Christchurch, New Zealand. In the current research, we use the GIS methodology for using orientation in pipeline damage assessment, and damage correlations are developed by evaluating pipeline orientations in the Christchurch water distribution system. This research focuses on axial ground strains in the directions of pipelines, which are considered as the main cause of damage related to primarily to joint failures. The 2011 Christchurch earthquake caused substantial damage to the Christchurch water distribution system. The data collected following the earthquake are unprecedented in size and detail, involving high-resolution light detection and ranging LiDAR, measurements of ground movements, and detailed repair records for thousands of kilometers of underground pipelines with coordinates for the location of each repair, as well as seismic, geologic, and geotechnical information. Both ArcGIS and QGIS were used at different stages of the study. ArcGIS is a commercial program by Esri, and QGIS is an open source software. All data were assembled in GIS with required attributes and appropriate coordinate systems and projections. The data involved both raster and vector components, which could be processed routinely in GIS. The figure shows the city of Christchurch water distribution system and repairs after the 2011 Christchurch earthquake, superimposed on areas of liquefaction and permanent ground deformation areas as characterized by LiDAR measurements. The majority of the pipelines and repairs belongs to asbestos cement, cast iron, and PVC pipelines. For the water distribution system, this study focuses on damage to water mains. It doesn't include repairs to smaller diameter submains and customer service laterals. There were 1,502 repairs to 1,730 kilometers of water mains, which are pipelines with diameters typically between 75 and 600 millimeters, conveying the largest flows in the system. The present study uses the most recent and improved water distribution network repair records provided by the stronger Christchurch infrastructure rebuild team. Well, we can see in this figure some examples in the water distribution system. The figure here provides the flowchart of the procedure used for evaluating pipeline orientation combined with lateral permanent ground deformations. It's a modified version of the methodology used by various researchers to incorporate pipeline orientation in pipeline damage correlations. The procedure works with three different sets of data, namely ground displacements, pipeline, and pipe repairs, following the process described here. Lateral strains, which characterize the effect of observed peak ground deformations on pipelines, are calculated from ground displacement. The repair rates corresponding to various strain levels are determined via GIS analysis performed on pipeline and repairs. This study uses LiDAR data of 4-meter spacing, as it is more compatible with typical pipe segments ranging between 4 to 6 meters in Christchurch. As discussed in Toprak et al. 1999, the scaling effect is important in pipeline damage assessment. The overall area of the resulting GIS lattice points and 4-meter polygons is about 74 square kilometers. Considering the dimensions of LiDAR coverage area is approximately 12 by 9 kilometers, these data create an enormous database with about 4 million data points with no data points on lakes, sea, rivers, etc. Each data point in the grid is characterized by coordinates and horizontal displacements, east-west and north-south directions. To calculate ground strains numerically, the finite element method was used with GIS and spreadsheets. In this method, a continuum is decomposed into a finite number of elements, and a systematic approximate solution is obtained via interpolation functions in terms of field variables defined at the nodes. Each element is connected to neighboring elements at common nodes. As shown in previous figure, the LiDAR data points form a square pattern and a square element 4 by 4 meter that compose the obtained data set and can be considered as a finite element network consisting of non-rectangular elements in finite element analysis. Well, if we go back to the figure here, we can see the enlarged square element from figure with displacement in east-west direction, U, and north-south direction, V, shown at corners of such an element. In essence, the LiDAR data points are taken as the nodes of the ground element. Also shown in the figure is a pipe oriented with an angle alpha with respect to axis. Because of uneven displacements at corner of elements, some deformations occur in each element. The evaluation can be performed of strains conforming to the pipeline axial orientation. The first step in such a process is to determine the orientation of each individual pipe segment with respect to defined Cartesian coordinate system. The second step is to calculate strains for each pipe corresponding to its longitudinal direction. The next step is to calculate repair rate corresponding to different strain levels and regressing the data to obtain pipeline damage correlations. It is assumed that the pipelines conform to the ground movements and experience similar strains as the ground. And here in this slide, we show the equations used during the process. Orientation of pipelines in an urban water distribution system naturally follows the layout of the streets and buildings. In this figure, we can see the orientation of all pipelines in the Christchurch water distribution system, as well as orientation of the pipelines in the liquefaction zone, which is a subset of whole city. The pipeline orientation is defined by angle alpha, which is the angle between x-axis and pipe axis direction, changing counterclockwise between 0 and 180, as shown in the figure. The orientation of pipelines were determined in GIS. The histogram actually illustrates the number of pipes in the east-west and north-south direction within plus or minus 10 degrees and are approximately equal and make up about 40% of all pipes. Similarly, number of pipes in the northeast, southwest, and northwest, southeast direction are approximately equal and make up about 30% of all pipes. The rest of the pipes are equally divided in other orientations, and the same trend is observed for pipelines in liquefaction area and all Christchurch. Calculating strains for the whole area at once was not possible due to GIS software constraints. To solve this problem, lidar coverage area of the liquefaction zone was divided into 31 smaller subregions. Figure shows these 31 zones superimposed on pipelines and pipe repairs. Separate ground strain analyses were performed for all regions and then were combined. The areas of the subregions were created as equal as possible, such that they will have about the same area. This dataset required a relatively long time for analysis. To develop pipeline damage correlations, first the strain map was combined with both pipeline and pipeline repairs data to determine the length of the pipelines and number of repairs corresponding to certain strain levels. Afterwards, the repair rate values with respect to strain values were calculated from the pipeline length and repair data. During the process, the screening criteria was used to determine appropriate strain intervals, which include sufficient pipe length to produce meaningful correlations. The data which satisfy the screening criteria were used to obtain the pipeline damage regressions. It should be noted that this process was performed on the assembled data from all 31 subregions, not on individual subregions. Like the process followed for the pipeline damage correlations for maximum absolute strains, similar screening criteria were used for the development of pipeline damage correlations with respect to axial strains. Previous studies showed that pipe material is an important parameter in the seismic performance of water distribution systems. Therefore, the analysis here were carried out separately with respect to pipe material. Because of the space limitations, only the correlations related to cast iron and asbestos cement pipelines are presented here. This figure and the following figure show repair rates and damage correlations with respect to strains for cast iron and asbestos cement pipelines, respectively. In addition to repair rate, pipeline damage was correlated with the damage pipe ratio, DPR, which is a dimensionless parameter obtained by dividing the total number of pipe segments needing repairs by the total number of all pipe segments in each strain bin. The linear regressions for the correlations provide a comparable and good fit of the data with relatively high R-square values. 4 different strains are used in the figures, namely absolute maximum principal strain, compressive axial strain, tensile axial strain, and absolute axial strain. The absolute axial strain corresponds to the maximum of the absolute of tensile and compressive axial strains. The range of the strains for which damage relationships could be developed varied as a result of the availability of existing data in these ranges and screening criteria. This figure shows that the repair rates and the regression lines for the tensile and compressive strains plot very close, indicating that the response of cast iron pipelines under tensile and compressive axial strains is quite similar. In this figure, we can see that AC pipelines have higher repair rate when exposed to tensile axial strain than the compressive axial strains. This can be explained by the weakness of AC pipelines, especially at the joints with lower resistance against pull-out when affected by tensile strains than compression when affected by compressive ground strains. Well, research work performed in the current study presents a GIS methodology that considers pipeline orientation when evaluating damage in large pipeline networks caused by ground deformation during earthquakes. The primary focus of the study is axial strains in the direction of pipelines because they are considered as the main cause of the damage, related primarily to joint failures. The geospatial analysis results reveal differences in the responses of asbestos cement and cast iron segmented pipelines under compressive and tensile axial strains. Accounting explicitly for pipeline orientation effects with respect to axial strain results in about the same statistical significance as previous studies focused on maximum principal strains. During ground movements caused by seismic excitation, pipelines may be influenced by axial strains as well as angular distortion. The combined effects of both these deformation parameters are under investigation as a continuation of the research presented here. Finally, I would like to acknowledge. Thank you for your attention.